I saw this integral on YouTube, and I have different methods to do it. Two methods. So I'm going to use two methods. I will just share with you. Now, the first method, I split this integral into two, from 0 to 1, and then from 1 to infinitive. Okay. Now let me discuss this integral separately. From 1 to infinitive, log square x squared plus 1 dx. And I use the substitution, let x be 1 over t. Then integral log x will be negative log t, right? Negative log t square. And this will be 1 over t square plus 1. Dx will be negative 1 over t square dt. When x equal to 1, t is 1. When x equal to infinity, t is 0. So this one equal to, let me write t for x, just dummy variables. This negative to switch the order, 0 to 1. Then this becomes a log square x, t for x. This time this one is 1. This time this one is x squared and the dx. Yeah, this one is this, right? Which is the same thing as this. Therefore, my target integral is equal to twice log square x and x squared plus 1. So this is my target integral, which is twice this integral. Okay, now we have a power series, 1 plus something, which is equal to sigma negative 1 to the power of n from 0 to infinitive, and the star to the n. Right, that is the power series, provided that the star absolute value must be less than 1. Well, to guarantee this series convergent. So our x squared is between 0 and 1. So the condition for the power series satisfied. Therefore, my I is equal to twice the integral. This 1 over this becomes the power series from negative 1 to the x, 1, and x to the 2n. Yeah. Yeah, I forget log. I'm sorry. I forget log. This is equal to twice log square x, then the power series, right? And x to n. Yeah, that's better. Yeah. So this one is equal to 2. I take this sigma out, minus 1 to the n. Integral 0 to 1 log square x e to the x, right? X, sorry, 2n, yeah, dx. That's better. Now let me discuss this integral separately. Okay, this integral 0 to 1 x to 2n log square x dx. Well, if we dump this one, then we get the I. Now this one is good. I can create some conditions for by parts. From 0 to 1 log x squared and dx 2n plus 1 over 2n plus 1. So this is the same thing as x to the 2n dx. Now I can use by parts, right? The constant taking out. U dv. So this one times x. uv minus v du. V is this. Du is a 2 log x times 1 of x dx. Well, when x equal to 0, when x equal to 1 is 0. When x equal to 0, it's infinity and a 0. Then you can do it to solve it by using L'Hopital's rule. I leave the job for you to do it, and then this end up with 0 minus 2 integral x to 2n and log x dx. Then this one equal to negative 2 to n plus 1 integral. Then I create condition for by parts again. This is a log x and a d x 2n plus 1 there y 2n plus 1. Right? This one is equal to, I'm changing the line, 2 2n plus 1 and uv, right? This taken out, so this taken out, it becomes a square. Right, but negative 2, this is taking out, so 2n plus 1 square. uv, u times v, this times this, minus v du, integral, v is this, du is 1 of x dx. Wow, it's good. So this is equal to, when x equal to 1, 0. When x equal to 0, use L'Hopital's rule. I leave a job for you to do, that's a 0. So it becomes, this one time this one is become positive 2n plus 1 square. This integral is x to n dx, right? That one's easy. 2 over, this one is a 2 x to n plus 1, 2n plus 1. So this will get 2n plus 1 cubed. This is equal to 1. Right? So this is this one, which is this one. Right? This one is this. So for my I is 2 times 2n plus 1 cubed. Okay, this one is this. And this one is equal to 4 sigma to n plus 1 cube. So that is my target integral. Just matter of the series value. Well, this one, according to Dirichlet, Dirichlet beta function is equal to sigma -1 to the n to n plus 1 to the power of s 0 to, okay. When s equal to 3, this is equal to pi cube 32. Okay, that is the beta function when s equal to 3. Well, our case s is 3, so this is equal to 4 times pi over 3. 8. Okay, this is my very answer for our integral by method 1. Okay, method 2. Method 2. X squared plus 1 dx. Method 2 start with substitution. Let x be e to the negative t. So this will equal to negative t square, right? This is negative square. This is e to the negative 2t plus 1. Dx will be e to the negative t times negative dt. When x equal to 0, t is infinitive. When x is positive infinitive, this is a negative infinitive. Then I'm using this negative to switch the order. Becomes negative to positive. Let me rewrite for t for x. So x squared e to the negative x e to the negative 2x plus 1 dx. Well, if this is my function x, this integrand function is x squared minus e to the negative x e to the negative 2x plus 1. If this is my f of x, my f of a negative x will be equal to no difference for square. Okay? This will be e to the positive x. This is e to the 2x plus 1. If I multiply both numerator and denominator by e to the negative 2x, and then f of a negative x would be equal to x squared. This will not become x negative x. This one time this is a 1. This time this one is e to the negative 2x. So this one is the same, which is equal to f of x. So my integrand function is the even function. If the even function, then this is equal to twice from 0 to infinity x squared e to the negative x e to the negative 2x plus 1 dx. Why? Because this is even. And then I'll rewrite this one as a 2 and x squared negative multiplied by 1 over 1 plus e to the negative 2x dx. I have to work out carefully. And this one, I can use the power function again because x is between 0 and infinity. Therefore, e to this negative 2x must be less than 1, positive. So this could be written as 2 integral x and sigma from 0 to infinity, negative 1 to the 1, e to the negative 2nx. Yeah, very good. So this one is this, by using power series. Then this one and that one can be combined. 0 to this one, x squared e to the negative 2n plus 1x. I forget the sigma notation. 2 integral, right, sigma negative 1 to the n and x squared e to the negative 2n plus 1x dx. Yeah, that's better. Wow. Okay, good. Then equal to sigma 0 to infinity negative 1 to the power of this one, and the integral from 0 to infinity x squared e to the negative 2n plus 1x dx. Wow. Okay. Now we have a gamma function. Gamma function, gamma over z is integral t to the z minus 1 and e to the negative t, right? And the dt. That's gamma function. Then the real part of z is positive. In our case, is true. So I try to use the gamma function. Now, see the parameter has to be matching. This, if this is a t, negative t, so that this must be t, and this must be t, this must be t, this must be t. So I just organize this way: 2 sigma from 0 to infinity, negative 1 to the integral t. What is t? T is this. So I just write 2n plus 1 times x squared. But I maintain the equal sign. I have to maintain an equal sign. So I divide by 2n plus 1 squared. So this is end up with x squared. See, it's a maintain equal sign. What's the technique of integration? Just changing the integral function to what you want. At the same time that you maintain the equal sign. Now this was e to the negative 2n plus 1. Good. This one has to be changed. This has to change it into d 2n plus 1x. To maintain equal sign, I just divide by 2n plus 1. See, it's equal. So then it's good because this is 2, right? These constants could be taken out. No, I'll write this way: 2 sigma 0 to infinity negative 1 to the n 2n plus 1 q. This one taking out integral 0 to infinity and 2n plus 1 x square e to the negative 2n plus 1 x and d 2n plus 1 x. Wow, this is good. So that just satisfy my gamma function. Something square, something e to something x, e to something. Okay? This is 2n plus 1x. Something square, something to a z minus 1, e to something, and then d something. So that is perfectly equal to 2 sigma negative 1 to the power 2n plus 1 to the cube. And this is gamma over 3. Okay? 3 minus 1 is 2. Well, gamma n plus 1 is equal to n factorial. Right? So this is equal to 2 factorial. This is equal to 4. Well, minus 1 to the n to n plus 1 to the q. This one is equal to, this is 4, right? This is 8 pi cube. No, 32, right? So finally it's equal to pi cube over 8. That is my result. Well, I hope you follow, and I hope you'd like it too. And it's a very nice method. Thank you.